Hello everyone. Today we shall discuss about a new thing that is Kepler's laws. And you see here what are the various factors we are dealing with Kepler's laws. You'll find it here that some of the important things you'll find in Kepler's laws. These are the important factors in Kepler's laws of motion. You see here these are the various factors of Kepler's laws of motion. Today we are going to discuss all these things about Kepler's laws of motion. You will find that these are the various things, various factors we are dealing with Kepler's laws of motion. So we see here what are the various factors in Kepler's law. Today we are going to deal with Kepler's laws of motion. You see here what are the various factors in Kepler's laws of motion that we are going to deal with today. Now here you see that what are the various factors in Kepler's laws of motion. Now first of all we learn about the various laws of Kepler's, and we know that in Kepler's law there are three laws in Kepler's laws of motion that we are going to deal with first. After that we learn the other important things. So first of all we learn the areas or learn the various laws of Kepler's laws of motion. You see, let us learn step by step the various Kepler's laws of motion. The first one, what is important is this one. The first one is that you see here what are the important factors in Kepler's laws of motion. You'll find here that these are the various important things in Kepler's laws of motion. First one, what we want to know is the Kepler's laws. In Kepler's laws, actually, there are three scientific laws describing the motion of planets around the sun, as seen below. So, we are discussing about Kepler's laws. You see here, these are the various Kepler's laws. These are the Kepler's laws. You find here there are various factors involved in Kepler's laws. These are three scientific. These are three scientific laws. Three scientific. These are three scientific laws describing the motion of planets, describing the motion, of planets, describing the motion of planets around the sun, around the sun, as given below. Then we learn what are the various other factors in Kepler's laws. The first one, what we call it as the law of orbits. The first one, what we call it is the law of orbits. This is law of orbits. Law of orbits. What is this law of orbits? Actually, all planets move in elliptical orbit when sun situated at one of the foci of the ellipse, as shown in figure below. What you can say that planets, all planets move in elliptical orbit. In elliptical orbit, all planets move in elliptical orbit with sun with sun with sun situated situated at one of the foci, at one of the foci. Foci is a plural of focus. Foci of the ellipse, of the ellipse, of the ellipse, as shown in figure, as shown in figure. Now you see here, suppose this is the elliptical orbit of the earth. This is elliptical orbit. You see here, we are taking elliptical orbit here. This is the elliptical orbit. And suppose this is the positions of the sun. Suppose this is P, this is A, and here there is S and S dash. This is our sun. This is S, and this one is S dash. S dash. And you see there are 2 points. One is at B point. This is B. This is B point. And this one is C point. We are joining these point. This distance from B to C is 2B. This distance from B to C is 2B. And this distance from P to A, and this is 2A. Now the closest point P is called the period. You see here, this P, closest point to the sun, right? This is the orbit of our earth, right? That means suppose this is orbit of our earth or orbit of any planet, and this P point is the closest to the sun. So you can say that the closest point P, the closest point, the closest point P is called perihelion, is called perihelion, and the furthest point A and the furthest point A is called aphelion. Here you see this point P is closest to the Sun, this is known as perihelion, and this A is farthest from the Sun and this is known as aphelion. So in law of orbits we will know that all planets move in elliptical orbit with Sun situated at one of the foci of the ellipse as shown in figure. And you can see here, and the closest point P is called the perihelion and the farthest point A is called aphelion, right? And what we find, the second one is the law of areas. So in Kepler's law, what we find in law of orbits, all planets move in elliptical orbit with Sun situated at one of the foci of the ellipse as shown in figure. The closest point P is called perihelion and the farthest point A is called aphelion, right? And the next point what we want to learn, that is law of areas. What is that law of areas? These are the few laws of Kepler's, laws of areas. In laws of areas, you'll find the line that joins the line, the line that joins any planet the line that joins any planet to the Sun sweeps equal areas in equal intervals of time, in equal intervals of time. This is the law of areas. Now if you find that here we are finding a elliptical path, and you see here we are making an ellipse here. We are taking ellipse here, and you see here how you are making this one, right? And we change the color to white. So we have taken an ellipse here, you can see here, and if this ellipse, suppose this is our Sun, this is our Sun, this is our Sun, and this point, this one, from here to here and from here to here, and if it is the farthest at any in this point, then we are getting this point, and also another point is here, right? And we take this as del A area, del A, and if we find the area, this area, that this area and this area will be same in law of areas. You see here that this area and this area would be same. I can see here, if we want to find the area of this triangle, this line for a small time, this is a straight line, and if it is straight line, it is the area of a triangle, and it also, if it is the time is very small, that is del t, then it will be time is very less. So you can say here that this is R, and the force is always toward the center, towards the focus, towards the Sun, that is the centripetal force. The planet P, as shown in figure, the planet P, the planet P, this is the planet P, this is the planet P, and this planet is moving from this place to this place P dash in time del t. Then we can see here that at a particular point the velocity is always tangential or perpendicular to this point, or you can say it as tangential. The velocity of the planet is tangential or perpendicular to this point. So the planet P, as shown in figure, planet P as shown in figure, as shown in figure, as shown in figure below, appears to move, appears to move slower, when it is further from the sun, when it is further from the sun, than when it is nearer, when it is nearer. So the planet P, as shown in figure below, appears to move slower when it is farther from the sun than when it is nearer. You can see here, it is nearer, moves slower when it is farther from the sun. It moves slower and it moves faster at this point. This is P, this is P dash. Here you see that there is long distance and same time interval is has to cover from P to P dash. Here the speed of this, orbital speed of this planet will be more than here. When it is further, it is moving slowly. When it is further, it is moves slowly. When it is near to the sun, it moves very fast. You see here, it moves very fast and it moves slowly. The area delay swept out by the planet. Now we will find the daily area. We want to find the area. We see how we want to find the area. You can find here that the area daily, if you remember this one also, the area daily swept out by the planet, swept out by the planet of mass m, in time interval del t. In time interval del t is given by that del A is equal to half into R into V del t. You can see here, if we find that the time is del t, short interval of time del t, and here you can find this distance is V del t, that is V del t. Therefore, this is the area of a triangle actually. You see, this is the area of a triangle, right? And we know that area of a triangle is, suppose this is ABC, A, B, C. This BC is the R, the radius, and AC is the height, and that is V del t, The area of a triangle is half base into height, that is half into r into v into del t. This is the area of the triangle. So here also we find the area of the triangle as half into r into v into del t, right? So if you write here as, now we know that v is equal to v, we know that velocity is equal to p by m, p by m. Therefore, in place of v, you can write p by m. Therefore, it is equal to 1 by 2 into r into place of v, we write p by m into del t. Or you can write del a by del t, that will be equal to half into r cross p by m. And what is r cross p? We know that r cross p is capital L by 2m. And this is L, what we call is the angular momentum, right? Where v is the velocity and L is angular momentum equal to r cross p. Where v is the velocity, where v is the velocity, where v is the velocity, v is the velocity, and capital L is the angular momentum, equal to r cross p. So what you are getting, that del A by del t equal to half into r or L by 2m. Del A by del t, what you get is L by 2m. L is the angular momentum and m is the mass. You are getting del A by del t as L by 2m. Now we learned that for a central force, we know that gravitational force is a central force. We have already discussed about it. That for a central force F, for a central force, F, for a central force F, which is directed along r, which is directed along r vector, that L is a constant. Angular momentum is constant as the planet goes around the sun. As the planet goes around the sun, Hence you can say, del A by del t is a constant. So the rate of change of area with respect to time is constant. Number 1. The law of areas can be understood. The law of areas can be understood. The law of areas can be understood as a consequence of conservation of angular momentum. Conservation of angular momentum which is valid for any central force, which is valid for any central force, for any central force. So this you have to know that the law of areas can be understood as a consequence of conservation of angular momentum, which is valid for any central force. And we have already discussed that gravitational force is a central force. Not only that, we have already discussed also that gravitational force is a conservative force. What is the meaning of conservative force? Conservative force means that it doesn't depend on the path. It depends only on the initial and final position, and the work done in a closed path is zero in central force. Then we learn other things also, that is number 2. A central force is such. Number 2 is a central force. A central force. A central force is such that the force of the planet, that the force on the planet, the force on the planet is along the vector, the vector joining the sun and the planet, joining the sun and the planet, So in areas of laws of motion, what we find here is two things. The law of areas can be understood as a consequence of conservation of angular momentum, which is valid for any central force. The central force is such that the force of the planet is along the vector joining the sun and the planets. And the most important thing is that of law of periods. And this is what we call it. Number 3 is law of periods. Law of periods. If you want to find the law of periods, what you'll find that now you see here, this is what we call it as the, for any central force F which is directed along R, L is constant as the planet goes around the sun, hence del A by del T is a constant. The law of areas can be understood as a consequence of conservation of angular momentum, which is valid for any central force. A central force is such that the force of the planet is along the vector joining the sun and the planets. And the third one is law of periods, that is the square of the time, the square of the time period, the square of the time period, the square of the time period, the square of the time period of revolution, revolution of a planet, the square of the time period of revolution of a planet is proportional to the cube of semi-major axis, cube of semi-major semi-major axis of the of the ellipse of the ellipse traced out by the planet, traced out by the planet, by the planet. So you can say that that is we can say that t square is directly proportional to a cube, where a is the same major axis, where a is equal to semi-major axis, and t is equal to time period. These are the various laws we have learned here about this one, that is law of periods. And what we find it here, you see here once again, that in the first case what we got, that the first one is known as law of orbits. You can find here that in law of orbits, all planets move in elliptical orbit. All planets move in elliptical orbit with sun situated at one of the foci of the ellipse as shown in figure. This is the ellipse we have found. This is the sun, right? So the closest point P is called the perihelion and the farthest point A is called the aphelion. This is aphelion, this is perihelion. You see, this is the closest to the sun, and this one is farthest from the sun. This is aphelion, this is perihelion, and this distance from P to C is 2b, and the distance from P to A is 2a, right? This is 2a. That means from here to here, this is A. This is same major axis, right? Semi major axis. This is the major axis is 2a, so semi major axis is A. Here also you see this is 2b, and this one from here to here is B only. So the semi major axis is equal to A. So what we find that in this is the law of orbits. All planets move in elliptical orbit with sun situated at one of the foci of the ellipse as shown in figure. The closest point P is called perihelion and the farthest point A is called aphelion, right? Now what we find that the second one is the law of areas. In the second one you will find that law of areas. In law of areas, the line that joins any planet to the sun sweeps equal areas in equal intervals of time. Suppose this planet goes from P to P dash, and the time it takes is del t, and you know that the velocity of any planets at this point is tangential to this curve, right? Therefore, suppose if you take this as a triangle, then this is straight line PP. This is for a very small time interval del t. This is straight line PP dash. Since the PP dash is straight line, we can say it as the distance of PP dash is V into del t, right? And if you take the area of a triangle, then area equal to half into base into height. Half base is R and height is V del t. Therefore, you can write half into R into V del t. The planet as shown in figure below appears to move slower when it is farther from the sun and when it is than when it is nearer. When it is nearer, it moves faster. When it is further, it moves slower, right? So we can say that the area del A swept out by the planet of mass m in time interval del t is given by del A equal to half into R into V del t. I know that V equal to P by M. Then in place of V you can write P by M. Therefore R into P by M into del t. Or if you divide this del A by del t, you will get half into R into P, R cross P by M. And R cross P is L. L is what? Angular momentum. So where V is the velocity and L is the angular momentum equal to R cross P, right? So we are getting this one. Now there are two things we can find from here. That is, for a central force F, and we already discussed that A gravitational force is a central force. So you can say that for a central force F which is directed along R, L is a constant as the planet goes around the sun. Hence del A by del T is a constant. The law of areas can be understood as a consequence of conservation of angular momentum which is valid for any central force. The central force is such that the force on the planet is along the vector joining the sun and the planet. And the third is law of periods. The square of the time period of revolution of a planet is proportional to the cube of semi-major axis of the ellipse traced out by the planet. So we can write it here as t square is directly proportional to a cube, where a is equal to semi-major axis and t is equal to time period. Right? So we have learned the all the laws of Kepler's laws, and we have found three laws. One is law of orbits, law of areas, and law of periods. Thank you everybody for watching this video. Thank you.